The name of this video is Volume Magnetization Current vector Jm model. That is, in this video, we are going to introduce a very powerful model to understand the properties of capital M by means of Jm. Okay, it's the same as in 242. In Phys 242, we define a capital J, which was the current in conductors. In this case, Jm is a current in magnetic materials. It is clear somehow that we need currents, because obviously magnetic materials, instead of electric dipoles, we are considering magnetic dipoles, at the basis of which there is a loop of current, so it makes sense. Okay, so dielectric materials, in fact, can be fully described by means, as we know, rho p, which is the polarization charge, or sigma p on the surface, and in general qp, which is the overall polarization charge. Whereas magnetic materials, as it turns out, can be fully characterized by means of a vector current intensity Jm, magnetization current, a similar vector on a surface. So of course this one is in a volume. If I have a surface, for example, it could be the interface between two different magnetic materials. That surface can be characterized by a current intensity density Jms, and in general, these are characterized by a current intensity Im. So this is the comparison between dielectric and magnetic materials. Now let's make a generic sketch of a region capital omega space in the three-dimensional Euclidean space. Let's take a cross-section within the region, of the entire region. So I cut it as slices, and so I see something like a cross-section of this type. Okay, so I just cut the region into two, okay? And so within this region, let's further suppose that we consider an infinitesimal area here, dA. So the aim of what we are trying to do here, if we call capital sigma this surface here, which is an open surface, the aim is to find the current DIM, the infinitesimal current intensity DIM, across the region dA, and so this is the flux, assuming stationary condition, as we already said before, and I'm going to reiterate about this in a minute, of Jm dot NDA. So this we have seen in Phys 242 is the definition of a current intensity in presence of stationary currents, okay? And we are assuming that on average, these currents, which are the atoms, in the atoms, the electrons are moving around the protons, these currents, this loop of currents are stationary, we assume, on average. So DIM, which is the current intensity, is clearly given by Jm, the flux of Jm, the magnetization current. And again, what is this Jm? Well, so if I have a loop of currents, I can have a loop of current, for example, here, that is partially on this side of the board, and the other part goes behind. So this loop of current crosses capital sigma, and it could cross dA on capital sigma. And so such a loop of current generates a Jm. There is a Jm associated with it. And the flux of this Jm through capital sigma, in particular to dA, if I integrate over entire capital sigma, I obtain the overall flux. That's my DIM, okay? So eventually I need to sum up, that is integrate across the whole region, capital sigma, and so I obtain the algebraic sum of all these currents. So some loops can have the current going inside in this direction, some loops in the opposite side, because they are all randomly distributed at the beginning because of the Maxwell-Boltzmann distribution. These dipoles are all random, so some of them will cross from left to right, some from right to left, And so this is the algebraic sum. So when I integrate it to find the overall IM, this IM is going to be the algebraic sum. Okay, so IM eventually intended as an algebraic sum in a continuum is given by the surface integral on capital sigma, open in this case, obviously, of Jm dot n dA. And this again has to be intended as an algebraic sum. Okay, so now, in order to understand this problem, we need to focus, is worth focusing on what in FIS 242 and also in some videos here in 342 I refer to as the skiing hat. So the way this works is that, let me do the usual sketch. So whenever we have currents, we need to think about this construction, right? Because we know that for currents, particularly steady currents, we can forget about the surface, like in this case capital sigma, and instead we can consider just the border of that surface. So let's look at this and let's resketch a border here. Let's call it, so this border here, let's say it's like this. This is our border, and suppose that this is associated with an area like this. So this area here is one of the possible infinite open surfaces which have gamma as a border, and let's say that this gamma is oriented in this fashion. This is our line gamma. So gamma can have an infinite set of open surfaces associated with it. Clearly, in stationary conditions, the border is what counts, so we focus on this border. So in general, by definition, if we pick a point capital P here, and there is an infinitesimal area dA around this point capital P, and this one is n, so n dA will be an oriented surface if this is dA, the area of this surface here, an oriented surface on capital sigma gamma. And from this point to this point, I can define this quantity as a dl on gamma. So there is a dA on capital sigma gamma and a dl on gamma. And again, that's what we are trying to go for. We are trying to forget about the capital sigma gamma and focus on this gamma, which we've done many times when discussing about currents in FIS 242. So in this case, for example, a loop of current which does the following. So it crosses here, and then it goes behind, and then like this loop of current is linked with capital gamma. There could be another loop of current in a completely different orientation, like that. So this one also would be linked with the line. And so in order to show the linkage, let's suppose that this is our opening point. And so here we would preferably dot it so that we know that we are behind in this region. Perfect, like that. This is also linked. So these two loops are two examples of loops which are linked. What are these loops? These loops again are the electrons moving around the proton of an atom, right? Or okay, so it's like the Bohr-Rutherford model. So I can have these loops which can be linked or not with capital gamma, and they can have any orientation you want. For example, a loop like this, which has a double crossing, and then it goes back here. A loop like this is not linked. So this one, it's not linked, and we discussed about this extensively in 242. So double crossing and not an even number of crossings obviously results in no linkage, and odd number in linkage. And these loops can have any orientation you want. Why is that? Because let's say 300 Kelvin, they are all oriented randomly due to the Maxwell-Boltzmann distribution when you begin. When then eventually you switch on an external field B naught, and this will orient them, like exactly for the electric dipoles in dielectric materials. Okay. So now that we have this construction in mind, what is the model that we need to use in order to actually describe the math associated with this concept? So the model is very important and is as follows. So the first thing we need to know about this model is that we are considering homogeneous materials, so the same material. So this means that we have all the same currents I. So each atom is characterized by a current I, and these currents are all the same. And in addition, we assume that these currents I are stationary, which, as it turns out, on average is a good assumption for all practical purposes. Okay, in addition to that, we know that the areas A are all the same as well. The area A is the area of one atom. Of course, the areas are all the same. So IA or INA, where n is the unit vector normal to the area. Of course, that's a dipole, and I can have many dipoles. So all these dipoles can be oriented in many different ways. So I can have the areas are all the same, but this one could be oriented like this could be oriented like this, like that, etc. So I can have all these orientations of these dipoles. This is an area A, and they're all the same area, but different orientations. And this is the unit vector n, and there is the same current I associated with it. So I and A is the dipole moment associated with all of these. Now, since they're all randomly distributed, we need somehow to define a reference direction. And so the way actually we proceed is as follows. So we define a reference direction in this fashion, which we call the normal direction. And so there could be some dipoles with an area A, which are angled like this. Then we project it down onto this direction, which we choose as a reference. I can choose any direction I want, really. There could be dipoles which are characterized by this direction, so they're parallel to the chosen direction here. Other can be normal to it. Another can be oriented in this fashion. Etc. Okay, so in this case, for example, all the areas are all A, all the same, but the directions are different, again, because they are randomly distributed at the beginning of an experiment. So this will be n, the direction of the first loop of current associated with an atom. This is the direction n2 of the second loop of current. This is the direction, let's say, of the kth loop of current. And this is the direction of the last loop of current, which we call n subscript capital NL, because capital NL is the total number of loops we have in this system. So now, since they're all randomly oriented, okay, so we have a material, there are atoms inside. So in each atom there is a proton and there is an electron or a cloud of electrons moving around in this simple model. Okay, so we have these loops of currents. They are all randomly oriented because we are at 300 Kelvin, Maxwell-Boltzmann distribution. So they're all randomly oriented. Some of them cross this line gamma, some don't. We need to choose a common reference direction, okay? So we choose, for example, the one of N2. It can be whatever you want. It can be not aligned with any one of them. So then, because the areas are the same, but since they are differently oriented, the projection on this in this perpendicular surface actually is the same, is different. So obviously this projection here is 0, and it's quite different than this one, which is also different than this one. So all these projections are obviously different. Okay. So in fact, to make it more clear, I should have done this a little bit larger, okay? Because obviously it's going to have the same area, so it has to have a larger cross-section. So let's exaggerate it a little bit to make it more clear, more evident that these areas are obvious. This is a clear case, and this one, let's make it a little bit more clear so that we have it, okay, this is a little bit too much. Yeah, like this, I think is fine. Okay, so this cross-section is obviously less than this cross-section because this happens to be parallel. When it's normal, of course, you get exactly 0 cross-section, okay? And this cross-section happens to be the same as this, even though, of course, the n is different. So this is the key of our model, okay? And so from this key of this model, okay, so the areas, we call them, this area will be A1, this will be A2, all perpendicular because they are projected. And then dots eventually, this one is AK, perpendicular. And finally, this one is A capital NL, the last one, perpendicular, okay? All the projections, all these areas here, 1, 2, 3, and 4 in this simple example here. Okay, so how do we find the mean value of M? We've seen this in the previous video. Well, the mean value of M is nothing but I, which is the same for all the current and stationary, the area A times N. Now, but what are these A and N? Okay, so here you need to be very careful. This is a convention. We write it like this, but in this specific case, following this model, it so happens that in this model, I, of course, is the same. That's the only one which we don't touch. But capital A has to be intended, capital A has to be intended as the mean value of all the A perpendiculars, which means, if you want to spell it out completely here, it's going to be the sum for k that goes from 1 to capital NL, all the loops, of AK perpendicular. So I take all the dipoles, they have the same area, but they are differently oriented, so effectively there is an effective area in some direction, which I choose as a reference. So these are all these projections. I sum them up in this fashion, and this, of course, has to be divided by capital N-L. So this is the concept of average. So this A is actually this, okay? Is in a mean A. I don't put mean, otherwise there are many means, because also N here, vector, this is the mean of all N Ks, which of course you can write in a similar fashion. So they have to be intended as mean values, okay? So effectively this really is I mean value of A, perpendicular mean value of N, but for simplicity we just write it as such, which is just easier to write, okay? So in this way here. Okay, so now let me recap this video a little bit. So here we want to study the model, so we want to study magnetization current Jm, and so we need to provide a model to do that. So in fact, magnetization currents on a surface or in the volume, as well as current intensities, represent effectively magnetic materials. Now, this is the way you compute under stationary conditions Im from Jm. So now let's look at it a little bit more in detail. So if I take a line gamma, so I have an object of magnetic material, and I take inside it a line gamma, which has an infinite set of sigma gammas associated with it, I take just a line within an object. How many loops, how many electrons of the various atoms, which forms loops of currents, will be linked or not with this line gamma? That's what we want to understand in the next video. In order to understand that, we need to realize that all these loops have the same area, same current, which is stationary in this model, because they are the same atoms, it's homogeneous, but they are differently oriented. And so we need to choose a certain reference direction to actually obtain the effective cross-sectional area of each of them, so the effective area of all of them, which is perpendicular, what I call it now here. Similarly, and so we need to average it out to find the average A normal, which I define in this fashion. So also the directions of these dipoles are all random, and so we need to average that as well. When I multiply the same stationary current times this average A times this average N, I obtain the mean value of M, which we will use in order to find this Im in the next video. That's it.